So I've had a lot of like first and second year students ask me about future methods courses. And I was just wondering what you think the prerequisites are for your clustered in the fall.
Ah, I would say that ideally they would have had some kind of general linear models course,
Okay.
regression, that kind of thing. Optimally, they would also have had a generalized linear modeling course because there is a unit in there where I do cluster data that is counts, and I think I have a binary example. But not everybody will have had that, so that one is sort of would be nice, but isn't strictly necessary.
Okay. Yeah, they've had two of the regular like OLS type intro classes. But when do you usually offer the generalized?
It will come back next spring.
Okay.
I am hopeful that I could offer it every spring because I view that class as fundamental to basically all of my advanced classes, especially for SEM because you have to know what a logit is in order to know how to do factor analysis on a logit. And it's also helpful to know what a logit is before you combine that with a multi-level. I would say that with respect to this course versus the fall course, I start the clustered class as if you've never seen a multi-level model before. I start it in the exact same place. But for those of you who are interested in taking the clustered version of this class, I would say doing it in the fall would be advantageous to capitalize on the fixed and random effects vocabulary that you've been working so hard to acquire, because all of that will be the same. But if you know of people who want to come but they didn't take this class, that's fine. I start it at the beginning and I do it from the same sort of perspective, but I'm able to get a lot further because there isn't the time component in the clustered MLM. Also, I wanted to note I am planning on doing the clustered class as a hybrid. So I am planning on being in person, as they want all of us to be. I don't know whether we'll be masked or anything like that. Nothing has been communicated to me from up above. But I'm also going to have a Zoom window open. So if you are somebody who is squishy about coming back and sitting with all of your classmates in person, then you can come via Zoom instead. Or if that just works out better for your schedule for whatever reason, that would be fine. There's two aspects of Zoom that I've grown to like, and I'm just realizing now I'm not doing one of them. The closed captioning, I have been told, is very useful, and so I like having Zoom available for that, as well as the chat feature. So I like the fact that each of you can send me questions and if you're feeling shy and you don't want to ask your question in front of everybody. So I want to maintain that as an option. So what I envision is you could be logged into Zoom while sitting in front of me so that you could use the question window or the closed captioning if you so choose, or we could just do it, the old fashioned way with, us actually talking to each other in person. But the SEM class for next fall has officially been canceled, by the way. It will come back fall of 2022. So, all right. Does that answer the questions about coursework and stuff? If any of you are interested in taking more courses in our program and are seeking advice on what would be useful or in what order they would be useful, I am happy to chat with you individually as well. Because I know that can be tricky. And it's also a function of degrees of freedom and timing. But speaking of courses, I am prepared to offer each of you a deal. I'm going to play Let's Make a Deal, no costumes required. So I have two deals. Deal number one, on Sunday morning, you should have received an invitation to do an evaluation for this course as well as all of your courses. And I have a deal that there are 29 of you in this class. If at least 6 of you fill out that course evaluation, I will give all of you 1 point extra credit. I can see how many people have responded, but I cannot see who it is. So you'll have to shame each other into participating if you want the collective good. So that's one deal. The other is related to that. It used to be the case that I was able to add my own custom evaluation questions to the school's forms, and they don't allow that anymore. So I have developed a Qualtrics survey based on your experience on this class that asks more detailed questions about specific things. And tomorrow morning, you will receive an email invitation to complete that Qualtrics survey. The way that it works is that I can see on my end which emails have completed a survey, but I can't see which responses are linked to which emails. So if you can complete that survey individually, I will give you another point of extra credit. So up to 2 points. And I do this for several reasons. One is that I'm asking for your time. I am asking for you to be thoughtful and to do extra work in providing me with this feedback. And so I think it's a fair thing to compensate you by giving you points. But I legit do care what you think, and I do make changes to the course iteratively based on feedback. And so even though I'm not going to teach this particular course probably for another 2 years, the feedback is often useful in designing the other courses that I do as well. So just as an example, do you know what the formative assessments used to be once upon a time? They used to be in-class closed note quizzes. Yeah, that face, exactly. Everybody hated them. They hated them with the fire of 1,000 suns. And that was like the number one thing was like, do not make us take these quizzes. They're not fair. And they make me stressed out. And the questions aren't exactly what I was expecting. And yeah, they hated it. So based on that feedback, I moved it to out of class. And then based on further feedback that the people didn't necessarily always have time to get the answers right, I made it in the way that it is now, where you get points for trying and we talk about it in class. So just as an example of one of the changes that I've made. So closed captioning, Qualtrics equals Cooltricks survey. What an accurate statement. Okay, thanks. I'm not sure exactly what that means, but it sounds like a positive comment. So anyway, synopsis. If 26 out of 29 of you complete a university course evaluation, everybody gets a point extra credit. If you take the time to additionally complete my separate Qualtrics survey, I will give you a point of extra credit. Because good response rates make for good measurement, right? Survey response rate is everything, and I can control that. Uh-oh. Am I gone?
You're back.
I'm back.
The frozen image was you with your thumbs up.
You
Well,
definitely jinxed yourself.
Do what?
You jinxed yourself.
I jinxed myself. I did. I see all of my things like give me like connection lost messages simultaneously, but I feel like I'm still talking. So, okay, but we're here. We're all here. Okay, great. So, do you like those deals? Are they good deals? Yes. And I looked at grades this morning. If you've done all your work, everyone is in fine shape. And I know that graduate school is sometimes a neurotic experience. Like you feel like you really need the A+. And so for those of you who need the A+, there's your chance to get it. But I do value your feedback. And I do think it's important to compensate you for time spent in giving it to me. So that's my thing. Let me show you something that I found this morning in the real world that I thought would be relevant for us to talk about. So I'm starting the screen share here. Am I recording? Yes, I am recording. Make sure that that's still working. Not my PowerPoint slides. That's not the real world. I wanted to show you this. This is the New York Times. So each morning I get a newsletter that says, basically summary of what's happening. And the first headline here, we look at the upsides and downsides of slow population growth in the United States. So here's the obligatory picture of adorable children. And then we get to the story. And here is the chart that they had in here. So I'm looking at this on my phone at approximately 6:45 in the morning. Coffee hasn't yet hit the bloodstream. And I look at this chart and I think to myself, what? There's fewer people in 2000 than there was in 1800? What? But no, that's not what this chart is displaying. This chart is showing the change in population growth. So the y-axis here, this is not population amount. This is population growth. otherwise known as the thing that all of you hate most right now, the instantaneous linear slope at a given occasion. The New York Times is showing pictures of instantaneous linear slopes. So the y-axis is the rate of increase of the population at a particular year. And the point they were trying to make is that this rate is declining. So a quadratic effect of time is in play here. What they are saying is that there is a negative quadratic that is taking the positive rate of increase and making it less positive over time. So I just thought that was sort of cool. And it looks very much like this is a linear function, although it's a little bit bumpy. But there is the extent to which the population growth is decreasing appears relatively constant over time. So then the rest of the article was about whether or not this is a good thing or a bad thing or some combination thereof. But I just thought I would share this. How often do you see instantaneous linear slopes in the real world? And because I had so many questions about that as an idea and how to make it, I wanted to just point out where this is coming from. You'll get a chance to practice this again in the last homework, but this is from example 6a, and the ingredients for how you would come up with a predicted outcome at any occasion, as well as how you would get an instantaneous linear slope at any occasion. So the same was true in the piecewise models, because the occasions I picked, I had intended to be part of only one section of the curve, such that only one set of slopes would be relevant. But generally speaking, your instantaneous linear slope is you give the estimate statement a 1 for that slope, and then 2 times the value of time for which you want that linear slope at what occasion. So there's the ingredients in how the New York Times would have made that picture as well. And so then the code to do that is shown afterwards here in each of the programs. And this code would have worked very similarly in your homework to get instantaneous linear slopes. Not everybody has finished it yet, so I can't go over it as a group, but I just wanted to point that out as a reminder of where this stuff is coming from. So yeah, decreased population growth. How about that? But we are talking about predictors. That's what we've been talking about. Shall we head back to that? Why not? Yeah, your last homework is about time invariant predictors. So it's actually taking the same story from homework 3, the random quadratic model, and adding 2 time invariant predictors to it. I think it's only 3 models, so it will be quite doable, is my hope. But we were talking about the process of adding predictors and which variants they explain. And we'll get a chance to practice that in the example 7b. But I have just a few more slides to go over in terms of strategies and a little bit about degrees of freedom in these models, which can be a little bit hairy. So I'm going to pick up here on slide 31 of lecture 7b, talking about strategies. So do you remember back in the days of linear regression? Back when that was a thing, and that was like the hardest thing you knew how to do? Just pause for a moment and let that sink in, right? There was once a time when a single level regression model was challenging for you. And now look at what you're doing, right? Craziness, growth. The same ideas that you were probably taught in thinking about regression apply at this level of complexity as well. So in thinking about how you would put predictors into a regression model, a logical first question would be, are they correlated at all? Like, is each predictor related to the outcome, and is each predictor related to each other? So the first thing that you would do is try to establish their bivariate relationships amongst the variables in question to try and get a sense as to what is related in the first place. Analogously, if I have a growth model that I plan to add multiple time invariant predictors to, my suggestion as to a process is to take that same bivariate mindset and start with one predictor at a time. And it goes in as a main effect, and it goes in as a cross-level interaction with any level 1 predictors that have random slopes. So if I have a random quadratic model, that means that I could have age as a main effect if I have time invariant age, age by time, and age by time squared. So you're going to have this, for instance, in your homework. And the logic of doing it for each time invariant predictor separately is so that you can answer the question, if a given effect is not significant downstream when you put multiple predictors in the model, is it not significant ever, like it wouldn't have been just when it was all by itself? Or is it not significant anymore because of collinearity amongst the predictors? Because those are two different things. So I like the idea of just getting the lay of the land, so to speak, for each predictor separately at a time. Okay, what does this predictor do in the model? What does this predictor do? What does this predictor do? And then combining them in some kind of fashion that answers your research questions would probably be the next step. The order in which they go in is dependent on the context of the study and the questions to be asked, but in general, I like to know what is a variable's bivariate relationship with the growth curve, and then what is its unique relationship after controlling for other predictors. So that's what I tend to do in practice. So then you have something like this. For instance, in the example that I'm going to show you, I have abstract reasoning as a time invariant predictor of practice effects. After I figure out what age does in the model, I might add reasoning to the model, controlling for age, and then potentially you could have these higher order interaction terms as well. So just as you would ask, to what extent does the effect of age depend on your reasoning ability? To what extent does the effect of age on the linear slope depend on your reasoning ability? To what extent does the effect of age on the quadratic slope depend on your reasoning ability? You can ask those sorts of higher order moderation questions as well. The sequence of predictors, though, is not something that I can tell you as a prescription that will always hold. It really depends on the context of what you're doing. Typically speaking, there are variables that people would think of as covariates that would just need to go into the model no matter what to be controlled for. And then additional to that are the predictors that you care about that make your study unique. That is often how it's phrased, but you may end up at a different place with respect to what is the best model, meaning it has all the effects that it needs and none of the ones that it doesn't if you start at different places. So I would discourage you from going about the process of trying to think of the model, like you're only going to have one, and think about candidate models that each might describe different aspects of the data. So this is something that is, it's like I said, it's not something I can just offer one standard for, because it really does depend on the context of the study. In terms of significance tests, cough, cough, quiz question. The idea of testing the influence of time invariant predictors, you can always look at each of the fixed effects that you add. So you can look at the main effect of the time invariant predictor, you can look at its interaction with time, its interaction with time squared, and you can get a judgment of those. But if you want to answer a more general question, like for instance, does age matter? In the previous example, like if I wanted to know what is the effect of age in predicting change over time, that would involve three fixed effects. So just as you can do in a single level regression model, you can ask for joint hypothesis tests of multiple slopes in these models as well. The first example I think that you've seen of this is the saturated means thing, another thing everybody hates right now. The idea of adding in dummy codes to test whether or not your fixed quadratic slopes adequately reproduce the means. The hypothesis test for that, where you lumped all of those dummy codes together to get a test, that's the same thing that I'm talking about here. It's a more general strategy. You can think of it as a multivariate wall test. Sticklers for that will say that that's only for chi-square, but not for f. But if you add degrees of freedom, then it's the same thing. And you can always do that regardless of which estimator that you're using. So that's a way to test multiple fixed effects at once that you can do in REML or ML or probably even in Bayes. You will see examples in textbooks that do likelihood ratio tests for this purpose. So the difference in -2 log likelihood after you add effects of a time invariant predictor, but just keep in mind that that's only accurate, let's go with that, for maximum likelihood. So if you're in REML, your models cannot differ in their fixed effects to do a likelihood ratio test, so that strategy doesn't work. But when might you do this? Well, for instance, let's say that I have a higher order interaction, like education by time squared, that's marginally significant. Is it worth keeping in all three effects? Because I'd have to have education, education by time, and education by time squared. Do they do enough to warrant keeping all three in the model, even though the top one is the only one that's significant? So a hypothesis test that lumps them together would help to answer that question. It also answers the question as to whether or not the overall increase in total R-square is significant as a function of the new set of fixed effects that you added, similarly to a hierarchical regression or sequential regression. So I'll show you examples of all of those as well. Denominator degrees of freedom. This is just some information about what these things are. The one that we're using in this class is Satterthwaite, and that's because it is the most commonly available across multi-level modeling packages. There are others in here, but I want to point out though that in these models, denominator degrees of freedom is not something that you can calculate by hand the way that it is in a single level model, because they're adjusting simultaneously for the sample size at each level as well as the amount of variability at each level. So in our method of Satterthwaite, if we have time invariant fixed effects, the degrees of freedom for those fixed effects are going to look more like level 2 sample size. The ones for level 1 will look like level 2 sample size if the level 1 term has a random slope, but not if it's fixed only. So you will see denominator degrees of freedom that look strange, and they differ from model to model based on the contents, and that's okay. In practice, denominator degrees of freedom for specific fixed effects are not reported. No one cares. What you would just say is a one sentence in the beginning of your results that say denominator degrees of freedom were estimated using the Satterthwaite method. The end. And so you would only need to report then the estimate, the standard error, and some stars or some p-values. At the end of the day, though, it doesn't matter too much. So just as an example here, if I use denominator degrees of freedom equals 20, the critical value for my t-test for my slope would be 2.08. But if I just pretend that I don't have denominator degrees of freedom and use a z, then the cutoff is 1.96. So as you get past, 20 cases, like period, in your data set, the effect of degrees of freedom goes away pretty quick. Where it really matters is for tiny samples. So like when you have 5 cases per level 2 unit and 3 level 2 units, like those kinds of designs is where this really starts to matter. So just some information about that for you. And then a summary. Words. So we're ready to see some examples. Yay? Yay. Yeah, it occurred to me that today might have been not the best day to talk about course evaluations, given how much you all hate me right now for making you do that last homework. But I'm okay with that, because someday you'll be happy that you got through it. I'm okay with that. All right, so let me get this one. This is what I wanted. Example 7b. This is a long one. I don't know how long it will take us to go through it, but I'm happy to go as quickly or slowly as is warranted. So the first half of this demonstrates how you would add time invariant predictors to piecewise models that have linear slopes only, because that's easier. And the second half of it demonstrates how to add time invariant predictors to models that have quadratic slopes, which is harder. So, are you ready? We're ready. Okay, let's do this. So the same example data that we've been playing with throughout the semester, change in response time across 6 sessions of practice for a sample of older adults where everybody has the same 6 sessions, so it's balanced time, time is purely level 1. Now we're going to see to what extent that improvement with practice, so the idea of change over time and response time, is moderated by chronological age of these older adults, a measure of abstract reasoning, which is a proxy for fluid intelligence, as well as educational background. So I've got 3 moderators in the story here. So as is always the case, step 1 is to set up your predictor variables. So in this case, not only do we need to code whatever slopes we're going to use to represent change over time, but we also have to center the time invariant predictors so that 0 is meaningful. So I'm doing all of this in one step at the beginning of my code, even though not all of these variables are going to be used right away. So for the polynomial models, I'm centering time at session 1. So session 1 is going to be the common anchor point across all of the models in this handout. I'm also creating the piecewise slopes that I'll be using first off. So I have slope 1, 2, which is going to capture the change in response time from session 1 down to 2. And then slope 2, 6, which kicks in after that point to talk about change from 2 to 6. And each of these in this example is going to be linear only. Then we have age, which I'm centering at 80, and reasoning, which I'm centering at 22 because that was near the mean of the scale. So somebody with average reasoning ability, 80 was near the mean of age for the variables, so I'm putting my reference point in the middle. By the way, my naming convention for any predictor is to put the centering constant at the end of the name. So age 80 to me means age centered at 80. That way I always know just in looking at my output who the reference group is based on the constants that are part of the name. So I have 2 quantitative predictors that we'll be examining as moderators of change over time. And I needed a categorical predictor so that I could show you how to do it that way. And these data didn't actually have one, so I made one. So note the caveat here in capital letters: for demonstration purposes only, I cut up this variable. In practice, you never want to take a quantitative variable and chop it up into pieces. It introduces measurement error unnecessarily. So I'm doing this just so I have a categorical variable to show you how that would look. So I arbitrarily made 3 groups for this continuous variable for years of education, where less than or equal to 12 years of education is the low group, 12 years to, or greater than 12 years up to 16 years is the middle group, and then past 16 years is the high group. And then last but not least, I am subsetting the data, kicking out any case that does not have these predictor variables or the outcome so that my sample stays constant throughout all of the analyses, and therefore my log likelihoods stay on the same scale. And I'm doing that because I have to, because multi-level models do not handle missing data. Each row has to be complete. Okay, SAS people, any questions on the coding here? Okay, Stata folks, same story. The only difference is that I had to manually make a quadratic variable for inclusion on the random line in those models. Piecewise slopes takes a lot more code. And there's my centering for the other ones, and my recoding of education into 3 groups. And I used the row miss function to identify a new variable as the number missing, and then kicked out based on the number missing greater than 0. All right, so this data, folks, questions on the code? No. All right, our folks, same story. We have time as the polynomial. For the polynomial models, we've got piecewise effects of session here, and then centering the other ones. I found a function. I learned a new thing to do this called cut. I don't know if you've seen this before. It is a way to cut up a quantitative variable. Somebody made a thing to do this. So you tell it the ranges. So like you start at 0 and cut at 12, go from 12 and cut at 16, and then 16 up to, I just put a max in there of 100. And then it makes groups from 1 to 3. And then right equals true is whether or not you want the boundary within that category or past it. So it's like less than or equal to 12 is that, and then less than or equal to 16 for this one is what that does. And then I figured out how to drop cases with missing data. And to be honest, I don't understand this code, but I was able to make it to work. How's that for transparency? I asked the internet, how do I kick out incomplete cases in R? And this is what it told me. So there is something here that clearly matters, because without this comma, it doesn't work. But I don't know what that something is supposed to be. And these refer to the order of the columns that I'm selecting for completeness across. That much I figured out. But this is analogous code to get complete cases. So, and then descriptive statistics for all three of the variables so that I could make sure that my data were correct. So any questions on coding these variables up in R? No? All right. Then away we go. So first model on page 3 is an unconditional baseline. So the first set of models here is going to predict change as a function of the two piecewise linear slopes. So the first thing that I got to do then is figure out how much individual variance there is for the time invariant predictors to capture. So this is kind of like the same idea as starting with an empty model in order to figure out what fixed and random effects of time you need. Here I'm starting with an unconditional model in which there are no time invariant predictors, so that I can get a baseline as to what the highest possible amount of variance is in the intercept and in each of the two slopes, that we will then see how much it goes down after adding in the predictors. Okay, does that make sense? So like this is my new starting point for like the worst you can do is to have no predictors, and we'll see how much better the model works after we add them. So I have in here the level 1 and level 2 equations. So we have beta 1 is going to hold how each person gets their own slope 1, 2. Beta 2 is going to hold how each person gets their own slope 2, 6. Beta 0 is the intercept as usual. And in my level 2 model, I have added labels here as to what each of these equations is predicting. So this is me trying to make the equation slightly more transparent by labeling what it's doing. So beta 0 is predicting the intercept. Beta 1 is predicting the change from session 1 to 2, and beta 2 is predicting the change from sessions 2 to 6. And each of these betas is structured similarly with a fixed effect first, which is whatever that term is on average in this sample, and then a U random effect for how each person's deviation to get to what their value should be. So how far off from average they are in their intercept, slope 1, 2, and slope 2, 6. And then I wrote out how one would compute a model predicted outcome using only the fixed effects. So I have y hat here is a function of the fixed intercept, the fixed slope 1, 2, and the fixed slope 2, 6. So everybody would have the exact same predicted values in this model because everybody has the same 6 possible sessions. Okay, with me so far? So how many fixed effects are in my model for the means? We'll do some finger questions here. We'll play count the parameters game. How many fixed effects are in my model for the means? Yeah, they're not red here because I didn't want to go to that much trouble. 3, yeah, the gammas. 1 fixed intercept, 1 fixed slope 1, 2, 1 fixed slope 2, 6. How many parameters are in the model for the variance? We see there's 4 piles of variance. I've got 3 U's and 1 E, so that's 4, but what am I forgetting? I'm trying to I'll do like a 2-headed arrow or something. Covariances, yeah. They're not in the equations because they don't contribute to a predicted outcome, but they are in the model. If I wrote out this model using matrices, they'd be in there. But I hate matrices. So I just don't think in them. I don't. I think in scalars, so I write it out this way. But so each of these U's, because there's 3 U's here, there's 3 covariances among them. So in total, the model for the variance has 7 parameters. 1 E variance at level 1. Why are you off your line today? 1 U0 variance at level 2. Why do some people start out slower than others? A U1 variance. Why do some people change between slope sessions 1 and 2 more quickly than others? And then U2, why do some people continue to change between sessions 2 and 6 more quickly than others? And then there are 3 covariances there. So 10 parameters to start with. So here's the code for my model. The outcome in this case is response time to the number match 3 condition. There's also a number match 6 variable in this particular data set that I use for multivariate examples. And I have my 2 slopes as fixed effects. I don't have to write the fixed intercept because it's implied. I have my 2 slopes also as random effects, and I do have to write the intercept in Sas because it is not implied. And I don't have a repeated line in this example. So I'm trying to save a little bit of space, given this is already a 36-page handout, by not typing repeated. Because in every model, the R matrix is going to be diagonal. All of these models assume that the E variance is constant across occasions and there's no covariance amongst the level 1 residuals. So that is what you get by default if you don't write anything. So that's what I'm using. Couple new pieces of code. I'll get to that in just a second. Let me do stata, folks. Your fixed slopes go right here. Your random slopes go right here. In stata, both the fixed and random intercept are given to you by default, so you don't have to type either of them. And in R, I think that is also true, but it comforts me to put the 1 in there. I don't know why, I just like putting it in there to remind myself that it's there, particularly when you have your contest statements, the rows of 0s and 1s, like it keeps the placeholder. So my fixed intercept is here, my fixed slopes are here, and then inside the parentheses, there we go. There's my random part of the model, so I have my intercept and my 2 slopes in there as well. Okay. Questions on the code so far?
Just in stata, can you remind me again, the C dot in front of the variable name is doing what?
It is treating it as a continuous variable. You don't necessarily need it, but if you are going to use those variables in lincom statements, I have seen that it yells at you if it's not a C dot. So I've gotten in the habit of always putting it there. As opposed to I dot, which denotes that it's a categorical predictor, that stata is going to make dummy codes for you. Okay, other questions on code so far? Okay, so there's some new about the comma. I believe the stuff before the comma tells R which rows to use after the comma if you want to filter by rows. Okay, that makes a lot of sense.
And columns.
Yeah, I knew.
Rows
Yeah, I
and
knew what you
columns.
meant. Yeah, so the first part being blank means use all the rows. I'm assuming.
Yeah,
Yeah, as opposed to certain rows.
from what I
Thank you.
read.
Thank you. I appreciate that. That makes a lot of sense, and I should have thought of that, but I didn't. I was just so happy that I could make it work. That I didn't
Usually
question
me.
why. You know, there's a saying like, don't look a gift horse in the mouth. Like if something is given to you, like don't be ungrateful. And whenever I can make R work, I'm like, I just want to like leave it and be grateful and not like make R angry with me by asking questions. So thank you for that. There are some new parts to all of these codes here. So this thing right here in Sas, the out PM statement. In stata, it is this line right here that is predict. And in R, let me find it, it is also predict. So those new things are going to generate a new column, either in your data or in a separate data set, that holds the y hat values from your model. and it's y hat predicted outcome using only the fixed effects. So I know that in R because RE form on here stands for random effects equals NA, which means none of them. So make a predicted outcome for each case in the data set, store it as a new column, do not use the random effects. In Stata, that's what happens by default, that it's just the fixed effects only. And in Sas, it's the fixed effects only if it's out PM. It's out P if you want the random effects included in there. So what I'm doing then in each of these programs is generating a new column in the data set that says what the model thinks the outcome should be based on the fixed effects. I'm then going to take that predicted outcome column, correlate it with the real outcome. That's going to be R. And then if I square that R, that is R squared. So that's what I called total R square last week. Simply the idea of how good the model does at predicting the outcome. So ignoring which level is which, just period. How much variance in response time do these fixed effects account for? That's what I'm asking. So I'm doing that in Sas for right now. So in Sas, what is happening is this is a new data set, and I'm naming it with the prefix pred, and then p-unc to me means the piecewise model's unconditional. And in that data set, I am then asking it to correlate the new column that's called pred with the old one. I actually wrote a macro in Sas that does this for you, but I'm demonstrating what the macro does in this step here. The same thing you can do in Stata with just the core function. And then I found some code to square the R for you. So it will take the R that's saved from this analysis of the pred p-unc is the name of the variable in Stata that goes into the data set, and then the original outcome variable, and then this is the R square. And then in R, I did the same thing by first estimating the correlation between the saved predicted column and the real one, and then asking it to square that correlation and print it for you. So the code is working the same way across those two programs. So the question then is, getting a baseline, how much of the variance in response time is due to just average change over time, period? Let's figure that much out, and then we'll see how much more we can get by adding time invariant predictors. Okay, with me? All right, so here are the results using Sas. I did not print the R matrix, the G matrix, or the V matrix, or V core because we don't need those necessarily. The covariance parameters table tells you everything that you need to know. But I did print G core so that we could get a sense of the correlations among the random effects. So in this case, they're all negative and moderate, so we don't have any potential problems with collinearity that we are going to have in the polynomial models, so that's good. And then these are the variance components from the model. These represent all of the variance that there is to be had in change over time, individual differences in the intercept, change from slope 1, 2, change from slope 2 to 6. So these are our new sort of baselines for assessing effect size for the subsequent models. And we know from the previous analyses in example 6b that both of those slope variances were significant and that we need everything. Here's my fixed effects. So at this point, the model predicts the same growth curve on average for everybody. People are predicted to start out at 1962 milliseconds to do this task at the first occasion. And I know it's the first occasion because of the way that I coded the slopes, because they're zeroed out when it's session equals 1. Minus 163 is the rate of change from session 1 to 2. So people are improving in their response times by about 163 milliseconds. And then after session 2, the slope changes to be minus 32 milliseconds a session. So they are improving still because the slope is significant, but they're improving less than they were. And so we would have already gotten a pseudo R square that explains how much of the level 1 residual variance these level 1 time slopes would have explained. But I can supplement that with a total R-square that we get from correlating the predicted outcome with the real one and then squaring that. So the correlation between response time as predicted by these two slopes with the real one, is the correlation is 0.19. If I square that, that comes to a total R-square of about 0.04. So about 4% of all of the variance in response time across people and occasions is captured by just average change over time. So a lot left, 96% to be specific. Okay. And so I have these fixed effects labeled for you here, as well as all of the variance components, so that you can figure out how they're supposed to change as a function of adding predictors. So step 1 here, age. In the cognitive aging literature from which the study was taken, you have to control for age. Doesn't matter if you care, but controlling for chronological age is the first thing that you have to do. So I'm going to obey the rules, and that's what I'm going to do first. So this is a study where the data are being collected over a 2-week period. So age is time invariant because it is the age they were when the study started. So it's baseline age specifically, and we're centering it at age 80, which was near the mean age of this particular sample. So because I have a random intercept, I put in age as a main effect. That's gamma 01 right here. Because I have individual differences in change over time from session 1 to 2, U1, I put in age as an interaction with slope 1, 2. So we're talking about these two terms so far. And because I have individual differences in change from slope 2 to 6, I put in age as an interaction with slope 2, 6 as well. So each level 1 term that has a random part is eligible, so to speak, to be predicted by the time invariant predictor. You can still put in the interactions if it's not, but just that's a little more dicey in practice. So these 3 new terms in my model line correspond to gamma 01, gamma 11, and gamma 21. As a reminder, the subscripts, the first number tells you which beta at level 1 you're predicting, and the second subscript tells you which predictor it is in that level 2 equation. So each of these new gammas end in 1 because age is the first predictor of the intercept and of each of the 2 slopes. So from the perspective of the syntax, it looks like a main effect and 2 interaction terms. And you can see the interaction terms in the way that I've written this as a composite model, so to speak, so removing the betas and filling in the fixed effects directly. The predicted outcome from the fixed effects would be given right here, where the first row is what we had before, and the second row are the 3 new terms that we've added. All right, and a whole lot of code after that. We'll pause on that. Okay, so stare at that for a second and tell me if that makes sense. So 3 new effects of one time invariant predictor of age. So we're allowing age to moderate each separate aspect of this growth curve. Question, why are tau and residual gone in the composite model? Because this is not the full composite model. This is only the y-hat composite model. So I'm describing how the fixed effects work together to create a predicted outcome I'm leaving out of this composite model the random effects and residuals because they're not going to contribute to the predicted outcome column that I'm going to be correlating with the real one. Yeah, so it's note that it's y hat here and not y. Or as someone, I think the other class said, why party hat? I hadn't heard that version before. But yeah, it kind of looks like a party hat as opposed to like, you know, a top hat or a fedora or a cowboy hat. So yeah, why party hat? Because you know what they say about statisticians? They know how to party. It's why party hat. Now this thing. This box right here. What I'm trying to show is now how each of the three predictors in the model is a linear, the slope for each of these three predictors is a linear combination of the variables that it interacts with. So if I wanted to say, what is the expected slope 1, 2 for a given person, I now have to know how old they are. Because slope 1, 2 varies as a function of age. So I have gamma 1, 0 as the main effect of slope 1, 2. And that is going to become conditional. So given that age interacts with slope 1, 2, this main effect right here, gamma 1, 0, that is going to be specific to what kind of person? Who is that the slope for? Simple slopes equal conditional effects, not marginal effects. So the main effect of slope 1, 2 now is a conditional main effect, or a simple slope. And it is conditional on somebody who is 80. And I know that because that's the only situation in which this term drops out, is if it becomes 0 and falls out of the model. So yes, this gamma 1, 0 slope is specific to an 80-year-old. The interaction slope of slope 1, 2 by age then tells me how slope 1, 2 changes per year of age. Same is true for slope 2, 6. The first part here is for an 80-year-old, and then gamma 2, 1 tells me how that slope changes across age per unit of age. And then I could go the other way. So I think the way that is most intuitive in thinking about time invariant predictors is to think about how the predictor affects the growth curve. So do people who are older change faster or slower? That way of looking at this. But any set of two-way interactions has another equally valid interpretation. So another way of thinking about this exact same set of interactions is how the effect of age changes over time. How the effect of age changes over time is given by this composite right here. So likewise, that term right there, the main effect of age, is a conditional main effect of age, a simple slope, if you will. At what occasion is that the main effect of age? When are my slopes going to zero out? Yep, it's the occasion 1. The first occasion is when both of those slopes are coded 0, and then only this term would contribute to the effect of age. So the effect at the beginning of the study of age is given by gamma 01. The first interaction tells me how the effect of age changes from session 1 to session 2. And the second interaction term tells me how the effect of age changes from session 2 to session 6. How I got this magic box right here, same rules as for any linear model containing interaction terms. For each of these simple slopes, you want to go into the equation, find all of the terms that contain that slope first. So for slope 1, 2, for instance, I found all the places in here that have slope 1, 2. I then factor out that common term and stick it behind. And then the linear combination that's left gives me the ingredients for asking for the simple slope for any value of the moderator variable. So I did that 3 times because I've got 3 separate predictors that are each moderated by another. Okay. Questions on any of that so far? So then the estimate statements. These correspond then to specific instantiations of these 3 simple slope equations. So for instance, if I wanted to know at a range of ages what the predicted rate of change across these sessions is going to be. So for instance, I figured this out for age 74, age 80, and age 86 because that corresponded to roughly plus or minus 1 standard deviations. So in thinking about change over time as the thing I care about, and age is the moderator of that change over time. That's the story here. So to get the slope 1, 2 at a minimum, I need the main effect. Keep in mind that these words that you're typing in the estimate statements, they refer to the gammas. The words refer to what the fixed effects are going to be in the model. The values that you put next to them refer to the multiplier. You fill in the variable. And so in this case, there is no multiplier of gamma 1, 0. So I just put a 1 there. Because at a minimum, I need at least this. So I'm trying to figure out what slope 1, 2 is going to be for somebody. At a minimum, I need the first one. That's why it's slope 1, 2, 1 right here. Then, the interaction term of slope 1, 2 with age, I fill in the value of the moderator. For whom do I want slope 1, 2? I want it for a 74-year-old. Because I've centered age at 80, I put a -6 there. Likewise, if I want it for an 80-year-old, I put a 0 there. Did I have to write that line at all? Nope. That is what the main effect of slope 1, 2 is going to be in the model. I write it here for pedagogical purposes. And because it's sometimes nice to have all your output in one labeled section. So SAS doesn't care what you type here. It insists you type something, but it doesn't care what that is. So you can write as many or as few words as it takes for you to remind yourself what you're estimating. So the way that I'm writing these is, first thing is, what am I estimating, colon, who am I estimating it for? So this is slope 1, 2 for a 74-year-old. Same exact structure for slope 2, 6, just swapping out those fixed effects in terms of the words that I typed here. Okay, with me? Now flipping it the other way. The model also tells me how the effect of age changes across sessions. So I am using the latter simple slope equation right here to get that. So I have the age slope at each of my 6 possible occasions. And 1 goes with age 80 because at a minimum, the age slope is a function of its simple main effect. And then the values that go in the interaction terms are the value that corresponds to time as it is coded in each slope. So, excuse me. So not which occasion it is, but how time is coded in your coding scheme. So the first column here that goes 0, 1, 1, 1, 1, 1, that's because that's what that column looks like in my data. Slope 1, 2 is 0 at the first occasion, switches to 1 at session 2, and then stays 1. Slope 2, 6 is 0 at the first occasion, still 0 at the second occasion because it hasn't turned on yet, And then after session 2, it turns on to index the change from there. So the values that go in here are entirely dependent on your coding scheme for time. So the same things happen in Stata. So I have Stata code for this, and Stata has something that Sas doesn't have. A shortcut. I know, I'm jealous. Stata has a function within margins. So margins is typically used to create predicted outcomes, but it can also be used to create simple slopes. So in Stata, these 3 lines that demonstrate how to get slope 1, 2 for different ages are all given by just this one line right here. dy dx. Does that phrase mean anything to you? Yeah, derivative with respect to x. Don't tell anyone, but we're doing like a little bit of calculus. Just a little bit. At least that's where I learned how to do derivatives, was in my calculus class. So I am asking for the simple slope of slope 1, 2 over a range of values for age, where the numbers in here, the first number is where the range starts, so start at -6. The second number is in increments of what? So start at -6 in increments of 6. And the third number is where you end. So start at -6 in increments of 6 up to 6 gets you -6, 0, and 6 in one line of code. The only catch is that margins doesn't have a small option so that you can use denominator degrees of freedom, but you can import them manually. So I had to look up what denominator degrees of freedom turned out to be in the other programs and then stick it in here. So the same thing is true then for slope to 6. You can do that in one margin statement, and you can do the same thing for the effective age across sessions 1 to 2 or sessions 2 to 6. And R, folks, you get a line of digits like that. Contest 1D. So,
Lisa?
yeah, go ahead.
Just with the margins for Stata, in the first line you've got C slope 26 equals 0, C slope 12, and then the second one, C slope 26 equals 1.
Which line are you reading?
Where it says margins after the 3 lim com.
Okay, this one right here? Or
Yeah.
yes. Okay, what's the question?
So C slope 26 equals 0, and then C slope 12.
Mm-hmm.
And then the next margins, you've got C slope 26 equals 1, C slope 26.
Yes.
I'm just confused about the pattern there.
Okay. So inside the parentheses, this is an at function, and it's telling you what to range over and what to hold constant. So in order for us to have just slope 1, 2, C slope 26 has to be set to 0.
Okay.
And then to get from, then this has to be, I think this is a typo actually. Yep, thank you. This is a typo. This should be 12.
That's what I wondered.
Yep, that's my bad. Thank you for catching my error. I'd like to pretend that that was on purpose, but I think we all know better. Can you imagine though, wouldn't that be a fun homework? I'll just give you code that's wrong and you have to fix it. No, that's not fun? Okay, well, it is realistic though, right? Because that's my homework, right? I open my email and there's code. Tell me what's wrong with it. So I've gotten practiced at that kind of processing. But yes, thank you. This was meant to hold this constant at 1. And I think, yeah, oftentimes what happens is that like I work with the code and then I paste it in the document and then I run the thing and it gets an error message and I don't necessarily remember to change it back in this document. So sometimes the code that's online will be different and correct because I knew it got me the wrong answer. But I will check to make sure the code that is part of the syntax files is correct for this now that I've fixed this here. So, okay. I was in R because we're doing this sort of in sections of the same idea. So this is how you get the simple slopes at each age. And I started working on this and I understood what I was doing with the contest 1Ds and I wasn't getting the answers right. Wasn't getting them right. And I know what they should be because I've got output from the 2 other programs. And I'm like, what the hell? And finally, I realized what had happened. So I am writing the model statement with spaces so that I can like keep the terms visually separate to myself. But note that in these, it is going to put them in order of main effects first and interaction second. So what happens in my subsequent models is that even though I'm going to list these in order of which predictor is which, it's going to reorder them. So the order of the values that corresponds here is based on the resulting order of the fixed effects in your output, not what you said is the order. I know. But the values themselves correspond to slope 1, 2 for this set, slope 1, 2, 6 for this set, and then the first interaction term, and then the second interaction term. And so I have labels over here for the print as to what each of these things is actually trying to estimate. And the reason, by the way, that I have print is because in the output for R, it doesn't show comments in the text output that I'm using, and so I'm turning these into titles so that it shows it. And then the age slope at each session has a similar structure where these are the main effects of age, these are the values of session as the moderator for the effective age. Okay. 310 already? I'm guessing I'm the only one who feels that way. You're like, it's 3:10. It's not over yet. Time flies when you're having fun, though. It really does. There's only one more thing that I haven't talked about yet, I think. This right here. Our friend contrast back up in Sas. This is going to give a joint hypothesis test for all 3 slopes involving age. So I can answer the question, does age predict response time? Yes, it takes 3 slopes to describe how age predicts response time, and I can lump them together. So the contrast statement in Sas is how we do this, where the commas are delineators for numeric degree. Nope, not numeric. Numerator degrees of freedom. So I'm telling it that I want 3 separate slopes tested simultaneously. If I left out the commas, it would try to add the slopes together and test that one combined slope. So commas matter. In Stata, it's the test statement right here. So the same idea where the parentheses delineate numerator degrees of freedom. And I'm making it explicit that I'm testing each slope against a null hypothesis of 0. And in R, that is this contest MD thing. So I am putting a 1 for the main effective age, then for age by slope 1, 2, and then age by slope 2, 6. And I'm lumping those 3 slopes into one joint hypothesis test. Good times. All right, questions, comments? No, we're saturated again. Under-identified. Cognition is under-identified. Mind is saturated. Time to go. All right then. Office hours start now. Let me know if you need anything. The next thing due will be a formative assessment, so you got a ways before you can have to worry about that. Otherwise, I hope to see you Thursday. So thanks for coming. Bye, everybody.